So you can imagine sitting here on the earth. And as your body is still for a moment, as if you can feel the strength of the entire planet pulling you towards it. And so we'll begin with the mantra that's been part of my regular practice for several years. Because in this mantra is the intention for the topic we'll get into today. So just listen and continue to notice the Earth's gravity.
Shanti Pritdevi Shantir Apam Shantiroshataya Shanti Vanaspataya Shanti Vishve Deva Shanti Brahma Shanti Sarvagam Shanti Shantir Evam Shanti Sapma Shanti Redhi Shanti, Shanti, Shanti.
So in my experience with mantra, there are many layers of effect. So one layer is the sound of the mantra as you recite it many, many, many times over an extended period. The effect it has on your body and on your mind. And as you begin to create context for this mantra, it becomes like a filter through which to perceive life experiences. So a translation of this mantra into English: may there be peace in the cosmos, peace in the skies, and peace on earth. May all the waters know peace. May all the herbs and plants know peace. May the great trees of the forest know peace. May all the forces of the universe know peace. The immense transcendent reality is peace. May all know peace and only peace. And may that peace come unto me. Om, peace, peace, peace. So Shanti is this word in Sanskrit for peace. And when I reflect on this mantra, I use also the filter of science to perceive the mantra. And so the first part for me represents an acknowledgement of a connection from Earth to the distant cosmos. The middle section, speaking of different aspects of materiality and acknowledging the forces that bind them together, all connected in the same way the Earth and cosmos are. And this connection is the immense transcendent reality. And some aspect of what we are and who we are is also this connection. So this is how we go into speaking about the universe, through the eyes of somebody who's been practicing for as long as she's been studying physics. In particular today, we'll focus on form. And the reason I chose this title was because the first time I heard the Heart Sutra, what stuck out in my mind was a little part that says, form is emptiness, emptiness is form. And that still stays in my mind. And so we'll talk about the expanding universe and stars and galaxies, but it will be with this lens of emptiness and form, how the two aren't mutually exclusive, that you can't understand one without a concept of the other. And in particular, the first part of the talk will talk about the universe itself. So the universe expands, and within the expanding universe, materiality is evolving as well. So this gives you an image of what we're talking about today. 95% of the universe is something we don't know. It has names, particularly dark energy and dark matter. But 5% of the universe is what we know as stuff. So the technical word is baryonic matter. So things that we observe and have a good idea about. The don't know section, there are some ideas, but it's not definitive. It's an important part of the universe, but we're not going to talk much about it today. And to give you a sense, this was a quote by Dick Tracy. If you shot a rocket through the galaxy, the chances of hitting a star would be 1 in 10 to the 22. So this notation of a 1 with 22 zeros after it, it's a very big number. If you put it under 1, it becomes a very small number. So most of the universe is empty. We're going to talk about the small 5%. But at the same time, we can't ignore the other 95. So when we look at the expanding universe, we can use this image as our reference. So what this shows is the early universe. There was a singularity, a part here where all of the universe was at one point. This expanded out. There was a sort of a gap here that we'll get into. And then things, some of that 5% started forming and evolving to the kind of universe that we see today. So what we're going to talk about is not so much the very, very beginning. We're going to talk about this sort of transitory middle part. And then the second part will be about how things evolved to look like what they look like today. So the Big Bang maybe is a word that you've heard. And the Big Bang essentially is a mathematical description of what happens if you follow the equations of relativity back in time. That the mathematics bring you to a singularity 14 billion years ago. So this means everything in the universe was in one place. What that means physically is a little harder to explain, and I think nobody understands, but that's an explanation of a mathematical description. And this was well known by the 1920s. Things didn't quite work out, and in the 1970s, something called inflation got added, which means that the first moments of the Big Bang were unlike the other 14 billion years, in that the universe expanded extremely quickly and then came into something like what we know. So last week we ended in 1905 with Einstein's 4 papers, one of which talked about special relativity. It took about 10 more years before results were published on what became a more general theory of relativity. And this is called Einstein's field equations. It's a representation of essentially the left side over here represents a curvature of space-time, Oh, sorry. My iPhone is a little delayed. Let's see. Sorry about that. And let's go back. The left side, the G term, talks about the curvature of space-time. The right side, this large T, is mass or energy. So anywhere in the universe there's mass or energy, space and time will be distorted. And this factor G talks about that. So this large lambda in the center that I've put a red square around is what Einstein called his greatest mistake. And a nice reminder by James Joyce, a man of genius makes no mistakes. His errors are volitional and are the portals of discovery. Because at the time that this equation came, the assumption was that the universe was static. So the universe wasn't expanding. And this lambda term is just a constant that comes out of the mathematics. This constant can be 0, can be positive, can be negative. If you assume the universe is not expanding, you can give lambda a certain value, and that lambda holds the universe still. This was something that Isaac Newton sort of waved his hand and said something is holding the universe together. And Einstein had a mathematical representation for it now. Turned out he was wrong, but for about 15 years, he had a term that held the universe together. So what happened in the early universe, in particular this sort of gap between the left and right side? And so the universe as we know it started about 375,000 years after the Big Bang. And something changed. So the first few 100,000 years, everything was a mix of energy, mass, so much energy that it was just a soup of particles and energy. Particles turning into energy, energy converting into particles, but so much energy that nothing could bind to itself. Everything was just moving. But as things began to expand, the temperature of the system cooled down. And it cooled down so that the kinetic energy, the movement of these particles, was slow enough that some of these particles could attract to each other and start to form. And when this happened, it was like a window of emptiness. So the form came together and there was space. So through that space, the residual photons, the light, was free and could move. So for 14 billion years, some of these original photons live. So this is what's called the cosmic microwave background. And this top graphic, I'll try my pointer one more time, see if it'll let me do it. Ah, there it is. So this top part is a survey of the entire sky put together. So this is a bunch of images put together. And what you see here, this blue light is reflections off of particles in our own solar system. So that was taken out. It's called zodiacal light. And so everything here is what you see in the sky, different light, galaxies, stars, etc. If you remove everything that is a source of light, there's still a background here. And this is what's called the cosmic microwave background. This is the primordial pervasive light throughout the universe. So 14 billion years and these photons have never come into contact with anything. And so for me, when I heard the Gayatri mantra, often used in yoga practices, the Gayatri mantra is a mantra to the all-pervasive universal light, remover of ignorance and source of knowledge. And maybe not the same light coming from that mantra, but a sense of that all-pervasiveness and a connection that resides today from the very beginning of the universe. So from the earth to the cosmos, a connection. So materiality, which we're talking about today, is relationship. So the only reason that anything, any stuff exists is because it has a relationship or a bond with something else. Otherwise, materiality doesn't really take off or form. And so this is one way of thinking about how materiality is. We think of 4 forces. There's more modern descriptions which are a little bit different, but this is a simple way to think about it. So the strongest force is called the strong force. So physicists, you know, we're very practical people. The strongest force is called the strong force. And it's what binds together the nuclei of atoms. So if you have 2 protons or a proton and a neutron, they bind together with this strong force. It is a very short range force. So this right-hand column tells you how far away the force reaches. So these first 2, the strong and the weak force, hold together the nuclei of atoms. And at a certain distance, they're pretty much meaningless. The last 2 are something we're a little more familiar with, having never lived inside of a nucleus: the electromagnetic force and the gravitational force. So electromagnetic force, we know positive repels positive, positive and negative attract. The strength of the electromagnetic force relative to the strong force is still pretty weak. But what's different about the electromagnetic force is it acts over an infinite distance. It decreases a lot over distance, but there's no cutoff to the distance with electromagnetic forces. Likewise, gravity is also with infinite reach. 2 masses attract each other. But the strength of the gravitational force is significantly less than all other forces. So 10 to the minus 40, this is scientific notation, which means a 1 with 39 zeros before the decimal point. So extremely weak compared to the strongest force holding together the nuclei of atoms. And I want to emphasize how extremely weak gravity is, because gravity dominates the universe, but it's significantly weaker than everything else. So I'm going to share a piece of nostalgia with you. This is a video from the 1970s from IBM. And like most physics students in undergrad get to see this at one point. So they have newer, fancier versions, but I wanted to share the original version, created in 1977 in IBM labs. And this video will give you a sense of how large 10 to the 40 is, which means it gives you a scale of sort of how much weaker the gravitational force is compared to the force holding nuclei together.
The picnic near the lakeside in Chicago was the start of a lazy afternoon, early one October. We begin with a scene 1 meter wide, which we view from just 1 meter away. Now, every 10 seconds, we will look from 10 times farther away, and our field of view will be 10 times wider. This square is 10 meters wide, and in 10 seconds, the next square will be 10 times as wide. Our picture will center on the picnickers, even after they've been lost to sight. 100 meters wide. The distance a man can run in 10 seconds. Cars crowd the highway. Power boats lie at their docks. The colorful bleachers are Soldiers Field. This square is 1 kilometer wide, 1,000 meters. The distance a racing car can travel in 10 seconds. We see the great city on the lake shore. 10 to the 4th meters, 10 kilometers. The distance a supersonic airplane can travel in 10 seconds. We see first the rounded end of Lake Michigan, then the whole Great Lake. 10 to the 5th meters. The distance an orbiting satellite covers in 10 seconds. Long parades of clouds, the day's weather in the Middle West. 10 to the 6th, a 1 with 6 zeros, 1 million meters. Soon the Earth will show as a solid sphere. We are able to see the whole Earth now, just over a minute along the journey. The Earth diminishes into the distance, but those background stars are so much farther away that they do not yet appear to move. A line extends at the true speed of light. In 1 second, it half crosses the tilted orbit of the moon. Now we mark a small part of the path in which the Earth moves about the sun. now the orbital paths of the neighbor planets, Venus and Mars, then Mercury. Entering our field of view is the glowing center of our solar system, the Sun, followed by the massive outer planets, swinging wide in their big orbits. That odd orbit belongs to Pluto. A fringe of a myriad comets too faint to see completes the solar system. Ten to the 14th. As the solar system shrinks to one bright point in the distance, our sun is plainly now only one among the stars. Looking back from here, we note 4 southern constellations, still much as they appear from the far side of the Earth. This squares 10 to the 16th meters, 1 light year, not yet out to the next star. Our last 10-second step took us 10 light years further. The next will be 100. Our perspective changes so much in each step now that even the background stars will appear to converge. At last, we pass the bright star Arcturus and some stars of the Dipper. Normal but quite unfamiliar stars and clouds of gas surround us as we traverse the Milky Way galaxy. Giant steps carry us into the outskirts of the galaxy. And as we pull away, we begin to see the great flat spiral facing us. The time and path we chose to leave Chicago has brought us out of the galaxy along a course nearly perpendicular to its disk. The 2 little satellite galaxies of our own are the clouds of Magellan. 10 to the 22nd power, 1,000,000 light years. Groups of galaxies bring a new level of structure to the scene. Glowing points are no longer single stars, but whole galaxies of stars seen as one. We pass the big Virgo cluster of galaxies among many others, 100 million light years out. As we approach the limit of our vision, we pause to start back home. This lonely scene, the galaxies like dust, is what most of space looks like. This emptiness is normal. The richness of our own neighborhood is the exception. The trip back to the picnic on the lakefront will be a sped-up version, reducing the distance to the Earth's surface by 1 power of 10 every 2 seconds. In each 2 seconds, we'll appear to cover 90% of the remaining distance back to Earth. Notice the alternation between great activity and relative inactivity, a rhythm that will continue all the way into our next goal, a proton in the nucleus of a carbon atom beneath the skin on the hand of the sleeping man at the picnic. Ten to the 9th meters, 10 to the 8th, 7, 6, 5, 4, 3, 2, 1. We are back at our starting point. We slow up at 1 meter, 10 to the 0 power. Now we reduce the distance to our final destination by 90% every 10 seconds, each step much smaller than the one before. At 10 to the minus 2, 1/100th of a meter, 1 centimeter, we approach the surface of the hand. In a few seconds, we'll be entering the skin, crossing layer after layer from the outermost dead cells into a tiny blood vessel within. Skin layers vanish in turn. An outer layer of cells, felty collagen. The capillary containing red blood cells and a roughly lymphocyte. We enter the white cell. Among its vital organelles, the porous wall of the cell nucleus appears. The nucleus within holds the heredity of the man in the coiled coils of DNA. As we close in, we come to the double helix itself, a molecule like a long twisted ladder whose rungs of paired bases spell out twice, in an alphabet of 4 letters, the words of the powerful genetic message. At the atomic scale, the interplay of form and motion becomes more visible. We focus on one commonplace group of 3 hydrogen atoms bonded by electrical forces to a carbon atom. 4 electrons make up the outer shell of the carbon itself. They appear in quantum motion as a swarm of shimmering points. At 10 to the minus 10 meters, 1 angstrom, we find ourselves right among those outer electrons. Now we come upon the 2 inner electrons held in a tighter swarm. As we draw toward the atom's attracting center, we enter upon a vast inner space. At last, the carbon nucleus. So massive and so small. This carbon nucleus is made up of 6 protons and 6 neutrons. We are in the domain of universal modules. There are protons and neutrons in every nucleus, electrons in every atom, atoms bonded into every molecule out to the farthest galaxy. As a single proton fills our scene, we reach the edge of present understanding. Are these some quarks at intense interaction? Our journey has taken us through 40 powers of 10. If now the field is 1 unit, then when we saw many clusters of galaxies together, it was 10 to the 40th, or 1 and 40 zeros.
Okay. So why is it weak is another question. Why is gravity so significantly different than everything else when we break forces up that way? We don't know is the answer, but one idea, particularly proponent of string theory support, is the concept of multiple dimensions. So if you imagine like you're in the Zen Center in a small room and you light the incense and it's very overpowering, and then you open some windows and it becomes a bit weaker, the odor. So is it possible that gravity is something similar? Are there other dimensions in which some of gravity's strength is being spread? Or is there something else? So the shorter answer is we don't know. If you want some reflections on multiple dimensions, there's a fantastic book from the late 1800s called Flatland by Edwin Abbott. Or the concept of interstellar to get a visualization of gravity that's very accurate. And Flatland helps you reflect on what it might be like to interact with a being from higher dimensions than ours. So it's a great and really subversive story and quite political. And it's very small and readable. It's about a circle who lives in a 2-dimensional plane. And he gets visited one day by a sphere. And there's a whole structure and hierarchy in, oh no, he's not a circle, sorry. The circles are the highest of their hierarchy, but he has many sides, so he's kind of up there. And the whole hierarchy of this 2-dimensional world is laid out. And I know he's male because the females are straight lines in this. It's a really fantastic book if you haven't read it. So he gets a visit one day by a circle, and this circle can change its shape. And the circle claims it can see inside this being and all of his friends, and he can see inside the houses. And so he takes this 2-dimensional creature on a visit to the 3rd dimension to give a perception of what that looks like. So a great piece of art. That's quite good description. So we come back to this Big Bang, and remember Einstein's original concept of the field equations were this term lambda that held the universe together. So what changed? So what made us think that the universe is not static? Because it really looked static. And the problem is that at this point, the universe was essentially 2-dimensional. So we had this celestial sphere last week, like a dome in the sky. And essentially, if you look up, there's no way to tell how far away things are without any more information. And so at this point, everything was essentially 2-dimensional. If we saw a bright thing and something that wasn't so bright, we couldn't tell if that bright thing was just closer or if it was intrinsically bright. So we needed a way to make the universe appear more 3-dimensional. And so it started with a group of computers. So this is what early 20th century computers looked like. They looked like women, because they were women, mostly women. Some of them highly educated, some of them extremely organized and very fortunate to have their talents recognized. These are stellar calculators at Harvard College Observatory. And I thought this quote was apropos. All women have stars, but they are not the same things for different people. But all these stars are silent. You alone will have the stars as no one else has them. And so the job of these computers was to take the data and make it into science, essentially. So the astronomer, this is Pickering, this is Professor Pickering's group, would go and take observations and then give the observations to these women who would then organize them. They would essentially organize the universe. And we still today, there's women in here who have laid the foundation of classification systems that we still use today in astronomy. The woman standing in the center is Henrietta Levy. And she figured out a really important thing to make the universe seem three-dimensional. She figured out a standard candle. So one of her projects was to look at variable stars in the Large Magellanic Clouds. So variable stars blink, they're variable, their light goes in and out. There was one particular kind of blinking star called a Cepheid variable, and they had a certain way of blinking, so you could know if it was a Cepheid variable by the way it blinked. And when she looked at the Magellanic Cloud is a group of stars that's basically all the same distance. So she looked at these blinking stars, how fast they blinked and how bright they were. And she figured out a relationship between how fast these stars blink and how intrinsically bright they were. So if you have two of these blinking stars, one is very, very bright, and the other one is blinking the same, but it's dimmer, you can figure out that the brighter one is closer to you, the dimmer one is further away from you. So it gives us a three-dimensional perspective on the stars that are out there.
She did that herself, observing through telescopes.
The women were not allowed to observe through telescopes at this time. So she took the data and studied all of the images from this. So in these days, it didn't count as science to make photographs into data. Turns out that's most of what astronomy is. And so that was her. She didn't take any of the, it wasn't until the 60s, which women were officially allowed to work at telescopes in the US. She did eventually become, or no, not her, sorry, Cecilia Payne. So some of these women became sort of the foundation, and the Harvard Observatory actually had some of the first female faculty members in astronomy after they were promoted from computer. But computers in the US were, in NASA, a lot of women were used, a lot of African-American engineers and mathematicians were used at the beginning of the space program as well. And the first people to actually use digital computers were these women who did the mathematics and the analytics and applied them. They were the first ones to write the programs. They were the first ones to really use the machines as well. So Edwin Hubble took this work by Henrietta Levy and he applied it to these nebulous things that we were seeing out in the universe. So in the late 1800s, there was a lot of work being done collecting fuzzy things. They were called Eidlin universes. And so Hubble looked at the Cepheid variables in a lot of these island universes to figure out how far away they were. And what he figured out is that the universe is not functioning exactly the way we thought. So he found this relationship. It's an empirical relationship between the distance that something is away versus how fast it's moving away from us. And what he found was that the further away something was moving, the further away something was, the faster it was moving away from us. And this is what's called Hubble's law. And the slope of this line is what's called the Hubble constant. And it's still, it's still being refined even to this day. But this isn't the movement of the galaxies themselves sort of naturally evolving away. This is the space between us and the galaxies expanding with time. So this is a fantastic representation of the raisin bread model, which I don't know why raisin bread became the standard for this explanation, but in the early universe, you can think of a doughy version of the universe. The raisins represent the stuff sitting within the universe, galaxies. As time went on, the raisin bread expanded, moving the raisins further away from each other. So for example, a raisin that's close to the center might move like a centimeter. A raisin further away from the center might move 1 centimeter per centimeter. So the velocity of that raisin moving out is actually faster compared to the raisins that are close to the center of the bread. And then I guess we're baked today because this is where we are today. So again, the Big Bang wasn't stuff moving into the universe. It was the universe expanding from a singularity out to what it is today. So it's not the same thing as how galaxies and galaxy clusters are evolving. That's a different subject. So one of the things to contemplate here is the models for the expanding universe. Last week after the talk, actually 2 days after the talk, I ran into somebody who was here and he asked about the big crunch. And that's a term for this point here. So if we started at some point and gravity pulls everything back together, we should logically come to a big crunch at some point. Or another model is sort of beginning and then extending forever. And this was sort of the model that Einstein was thinking of when he developed the negative lambda that he used in the initial equation. So after Hubble's work and Levy's work, they came up with an idea of an expanding universe by setting this lambda term in the equations equal to 0. So that was what Einstein did. So that was a mistake putting it in there in the first place. It should have not been there because the universe is clearly expanding. But upon further work, long after Einstein has left us in the 1990s, we realized that not only is the universe expanding, but it's actually accelerating, getting further and further away as it expands. So it will never come back to a big crunch. It will continue expanding, which has a lot of other implications. If everything keeps moving further away from itself, will we just be one big homogeneous mess? Yeah. Not collapse, but there's the heat death of the universe. That's what they call it, where everything moves to maximum or minimum entropy. So it's just everything is just one continuous form, expanded out through time. Oh, good. Some lingering questions. So how can the universe just pop into existence like this Big Bang? It's a natural thing to ask. We're going to talk more about time next week, but the concept of popping into existence assumes that time exists and it exists in the way that we perceive it. So 2 different points. Perception of time may be very particular to our human experience or our understanding of the universe around us. It may be limited by a time sensor we have within us that's faulty. Another, I always like to credit good movies. Arrival is another example of a fantastic work that looks at how our concept of language can even affect our concept of time. And they have this Zen circle sort of all throughout the movie, which is quite nice. And energy. So if the universe has energy, it can never have been created without violating the laws of physics as we understand them. So if the universe has energy, it has always been in existence. In what capacity? It's not clear. There may be no energy in the universe, which I think has a whole other philosophical implications. And the designer question. All of the mathematics, at least as we understand them now, requires nothing additional from outside of the universe to create the universe as we see it today, at least that we consider. So the universe is self-contained, essentially, through these mathematics. Doesn't need an extra energy, it doesn't need an extra push to come into what we see today. So this is an image just to stop for a minute and look at. This is the ultra deep field from Hubble Space Telescope to give you a sense of the vastness of it all. So in this photo, the way that I was taught about it, and I'm not sure if it's this snapshot, but it's similar. So in the US, we have a 10-cent coin called a dime. And on this dime, there's a head, John F. Kennedy. And in his head, there's an eye. So if you were to hold a dime out at arm's length, the size of this square is about the size of the eye in the head of John F. Kennedy on this little coin. So it's a very, very small fleck. And what this image is, this is the Hubble Deep Field. And what it was early on in the Hubble telescope, the director of the telescope had some discretional time. So he could use the Hubble telescope to look at whatever projects he wanted. And so he turned the telescope to the darkest part of the sky and took a picture. So this is the darkest part of the sky, and this is what you find. In this picture, there are 5 things that are stars. Everything else is an extended body, is a galaxy full of billions of stars. Much of it empty, but still full at the same time. And so part of the motivation of this talk is an experience I had with this vastness and a practice that I developed as part of it. So I started studying physics around the same time I started tuning into spiritual practice. When I was about 17, I took my first physics class, and I had the fortune of being connected with a martial arts community where I was. So these 2 things were always parallel for me. I was doing one and doing the other, but they seemed very separate in the kind of mindset required for the 2 of them. And a few years ago, I sat with a teacher and friend named Mario Tanavaro, who teaches in the Buddhist tradition. And we had a day of practice and sitting in meditation. He just said the words, "Let your mind expand without limit." And it did. There's no words to describe the experience, but it was the first time that this astronomical learning sort of awoke and came to life in a different way for me. And so this word vastness is the closest I can come to explaining the sensation. And this photo for me sort of embodies that sensation.
So that's exactly, that's the reality of what would be seen. You had a super great eye standing out. A lot of times when we see, that was a question, I actually didn't tell them. Because we see things like something will be reported, the signal from some nebula or something, and they'll say artist's rendering.
Yes.
That it doesn't look, or it's a recreation, artist's imagining of this starburst or gas. But that is not a retouched.
This is not an artist's rendering. This is optical wavelengths, which means your eye could capture it. If your eye could capture enough photons. So this is also a longer exposure. So this is a photograph requiring with some time with the exposure open so that the photons can come in and fill the space. So your eyes would never be able to capture this, but it's an advanced eye. That's what reality looks like at optical wavelengths, because the advanced eye can see much more than that. And so sometimes these artist renderings are to try to put into words, into images that our eyes understand, things that our eyes can never perceive. So the evolution of form. So how did this 5% become to look like what it does today? And we begin with light. So one of my teachers, Gary Kraftzow, said this once, and it stuck in my mind. We do not see light. It is because of light that we see. So we do not see light, but because of light, we see. So light interacts with our eyes, triggers a signal to our brain, which allows us to see things. But we never see the light. It's just a mechanism of transmitting information. And this is an English version of part of the Gayatri mantra I mentioned earlier. So meditating on the glory of the light that illuminates the universe and is the embodiment of knowledge, remover of all darkness and ignorance, and a request that that light fill us. So an important question to consider is, where does light come from? So light comes from stars and things like that, but at a really precise level, where does light come from? And it comes from charged particles. Charged particles move, releasing a photon if it goes to a lower energy state. This is a picture if we imagine atoms like billiard balls with particles moving around. If, say, the electron moves from a high energy state to a low energy state, it has to release some energy. That energy comes out in the form of a photon. So when you see light, you're seeing the vibrations of atoms. Punkt. That's it. You're just seeing the vibration of atoms. And somehow that makes reality for us. You're seeing the vibration of atoms. So this photon is not mass. It's not part of this material structure. It's empty. And so emptiness arises from this form. The electron moves, it produces this emptiness. Another book, Alice in Quantum Land. If you don't want to really understand quantum physics, but want to kind of laugh about quantum physics, it's quite a good book. And it's pretty accurate too. So this is how we use the nature of light to understand what materiality is made of. This is called spectroscopy. And forgive me, but I spent like 5 years working on this stuff, so you have to listen to at least 2 slides about it. So if you have a source of light here, and you shine it through a prism, you get a rainbow. That's something we've hopefully all seen. If you have a cloud of cool gas in front of the source of light, if you look at the rainbow, there will be holes in it. And so just like in the previous slide, an electron losing energy produces a photon, which is what's happening here. If a photon comes in to a low energy electron, that atom can absorb the photon so that the light from that source that's originally sending out the light is losing part of its spectrum. And each atom has a distinct fingerprint of holes that it leaves in the spectrum. So for example, this is my version. So this is like a Tammy-shaped hole in the light. This is what's happening in spectroscopy. You're just looking for the shape to figure out what's coming. You want me to stand back up there, the Tammy-shaped hole? There, that's probably a little bit better. There you go. Can I? That's it, yes. So the first person to use this understanding, and the reason that there are lines, distinct lines, is because of quantum mechanics. So the electrons move only from one particular state to another, and that particular state jump corresponds to a particular wavelength of the photon that's released. So the quantum nature of atoms is what causes holes to form in a certain pattern. And the first person to do this was Cecilia Payne in 1925, also at Harvard. And she actually became the first female professor of astronomy and eventually chair of the department. And she used this knowledge of spectroscopy and applied it to the sun and to the universe in particular. So she was the first person to know what that giant ball in the sky was after all of human history. And it turns out it's mostly hydrogen. And she didn't believe her own results for a couple of years, but eventually she got confirmation. So if you look, what it actually looks like to do this kind of work is something like this. This is a spectrum of the sun, and you can see there's many holes in the sun. And this is called a high dispersion spectra. And the people who work in this field have a particular personality trait, I have to say. They're very gentle people, they're very quiet people, and they sit with their high dispersion spectra and work on it for a lifetime and find out some really interesting things about nuclear physics along the way. So when we look at these holes in light, what we find is that 99.9% of the universe is basically 2 atoms, hydrogen and helium. So the first and second particles on the periodic table of elements. So everything else, everything that we are used to as being normal, is really just a bit of dust in the universe. So it's 5% of everything is basically hydrogen and helium, if you're looking at atoms. And then tiny, tiny, small part of that is everything else that we know of as life. And hydrogen and helium, they're so plentiful because at that moment of separation between light and materiality, the first atoms to form were these simple atoms. Everything else was formed inside of an intense oven called a star. So the first stars formed, and they were all basically made out of hydrogen, and still 75% of everything is hydrogen today. The other 25% is helium. And so there is generations of stars out in the universe. So the first stars that formed, the first particles were able to be particles, to be atoms. And with enough time and enough space, some of these atoms began to stick together, and gravity began to slowly take over. So things started becoming bound in clumps. So these are some actual images, but I have a little touched up, of M16 pillars, gas pillars. So there's big clumps of gas, and these clumps of gas are nurseries for the first stars, or for stars in general. So what happened is the first stars were born. Inside, it became so dense and hot that the hydrogen could no longer stay stable as hydrogen, and hydrogen thermonuclear fusion began to take place. So hydrogen began to convert into helium, and as stars evolved more and more complex elements were created in the center of these stars. And the first generation of stars were quite big, which means that they created a lot of heavy elements and eventually exploded. So these heavier elements produced in the center got spit out into the dust and gas in the universe. And then the second generation of stars formed out of that dust and gas. So the stellar archaeology that we do to understand about the ages of stars has to do with how much of these heavy chemicals, heavy elements are in their atmospheres. Because the atmosphere of a star is the same dust that it was formed out of. So when we look at a star, we're seeing basically its primordial composition from the outside. But stars like our sun have a lot of things like iron and calcium, heavier elements on the outside, because it's a later star. It formed out of the leftover bits of the first stars that exploded and put these heavy elements out there. So this is the sort of theoretical lifetime of a star. It starts out in this sort of gaseous state. Once the center gets so hot and dense that nucleosynthesis begins, it becomes a star. The outside doesn't look very different. It gets a bit hotter. This is a star like our sun. And all of this transition, this takes billions of years for stars like our sun. Nothing much is happening until the star runs out of hydrogen in its core. And it starts to burn things a bit differently in the center. And that causes some changing in the outside, so it becomes what's called a red giant star. And when our sun is done being a red giant star, it'll cool off, become what's called a white dwarf. Depending on how much gas there is at this beginning phase, it will determine how this life cycle turns out. So stars that are very heavy won't end up sort of cooling off into a white dwarf. There'll be supernova explosions, possibly neutron stars, black holes come out of this kind of process. And through this development and explosions later in life in these stars, we get the food and the soil for the next generation of stars. So stars like our sun, to give a sense of scale, this is about the size of the Earth right here. Stars like our sun is pretty new in terms of the universe, only a few billion years old. But the way our sun formed was through this. This is an artist's rendering, by the way, if you can't tell. This is a protostar. So our sun formed something like this, a large clump of gas with some slight rotation. That slight rotation led to what became like a disk around this early star. And out of this dust and gas came all of the material for all the planets in our solar system. So all prospects of life or any kind of planets is just the leftover bits from our sun. And to give you, so this is not to scale, obviously. The sizes are to scale, but the distance not. We have these inner planets here and these outer planets, which look different. And again, this has to do with balance of forces. So the inner planets are quite close to the sun, and they couldn't hold on to all their gas. So all that was left was a hard rock, essentially. So the heaviest elements that helped form our star are all that was left in the Earth and the other inner planets. And these larger planets are quite a bit further out and a little bit cooler and could hold on to a lot of gas. And there's a lot of noise now with some recent observations that there's likely another one of these gas giants somewhere out in the universe. I edited Pluto out of this drawing because this was an old drawing. No offense to Pluto. So, because Pluto is really not a star, well, or not a planet. But, so the extent of the solar system is not fully known either. But what we know is that all of the planets formed on this disk. So this was a point against Pluto in the status for planets, that the orbit of Pluto doesn't match the orbits of planets. So we just sort of have definitions. The definition of a planet is they form along this disk of dust that was created out of the leftover bits of the formation of our star. So moving further out, so now we're sort of taking this powers of 10 journey, but a little slower. So moving out further, we can see the extent of the sun's atmosphere. So all of the planets are in here. This is a picture from about 2005, but I love how it represented what was happening. Because Voyager 1 is now somewhere out here, and Voyager 2 is just on the border of the heliosphere. So this heliosphere are essentially a bath of charged particles being emitted from our sun, or carrying the energy of the sun. And these charged particles protect us from interstellar radiation. These are the same charged particles that cause storms once in a while that knock out satellites and things like that. But it's protecting us from things happening in the interstellar medium. Voyager 1 is now getting hit with the interstellar radiation and still able to send us back signals after about 40 years. And Voyager 2 is almost to the cusp of it. And this drawing is not the most accurate because for about 10 years or so, Voyager 1 was on the cusp of hitting the edge of the heliosphere, and it just didn't find it. It kept getting bigger and bigger. So actually, this was much bigger than we expected it to be, the heliosphere. But it's what allows us to, for example, have life without being destroyed by radiation. And when we look at things like planets to look for signs of possibility of life, we have to look at things like this. What's the protection that the local star offers the planet, affords the planet, so that life could begin? Many stars, actually most stars in the universe, don't form sort of off by themselves. They form in clusters because this clumpy nature of gravity. Things pull together and formation starts from there. So this is a star cluster. And it's the most common way that we find stars. And because all of these stars essentially formed around the same time, they become a great laboratory for looking at star formation. We look further out, a collection of star clusters and individual stars, and we see the Milky Way. So the Milky Way here, our sun lies about on this point. And the Milky Way is a barred spiral galaxy. And we have a better and better understanding of how our galaxy looks from above. And in particular, sort of the newest awareness is that galactic evolution is a form of destruction. So we have our Milky Way galaxy here. And what we're finding is that there are streams of stars surrounding the galaxy. So these streams were either clusters of stars or even small galaxies in themselves that are being ripped apart by the gravitational force of our galaxy. So it may be, but this is how all galaxies form, essentially destroying things to create something new. So the galactic formation is really just a description of destruction, most likely.
The gravitational force of our solar system is the sun. So it's the sun
No, this isn't the solar system. This is the galaxy. So the center of our galaxy is a supermassive black hole. And there's also gravity from all of the stuff, all of the stars, all of the clusters as well. So the black hole in the center is the source of is the center source, essentially. But everything is pulling at everything else because it's how gravity works. But it's all being centralized because that's gravity. One pointed always to one place in the center. No, the sun is over here. The center of the galaxy is here. So there's a supermassive black hole here with lots of stars spinning around it. And everything else is essentially, the formation and the structure is essentially a relic of what's happening in the central part. But everything, because gravity is complex, everything is acting on everything else. But the trend with gravity is always to the center, always back to the center. And even to the extent of these faraway objects, because interaction at this level is not touching. Nothing touches anything else. It's just the pulling. Our nearest large neighbor, another spiral galaxy called the Andromeda Galaxy, M31. It's one of the few galaxies you can see with the naked eye without a telescope. If you go to a really dark part of the sky, it's about the size of your fist in the sky, so it's quite extensive and faint, and it's just a beautiful. So the Milky Way galaxy and M31 are two types of spiral galaxies. These are a different kind. There's actually several different kinds. There's a whole classification system that these computers came up with. And these are elliptical galaxies. So these don't have the dust and the spiral arms like our galaxy. They're big balls of stars, essentially. And what we think is happening is that these galaxies are just further along the evolutionary cycle. So as everything is pulling on everything else, all of the dust gets used up to form stars, and everything becomes spherical. Back to the Greeks again. So the Greeks had this concept of a sphere as the perfect embodiment of nature. And if we look at older galaxies like this, we see that same concept. And so we have something called the local galactic group. And this is our Milky Way with a bunch of dwarf galaxies that orbit the Milky Way. And Andromeda Galaxy with all of her dwarf galaxies as well. And there's a little bit of a problem with what we see, is that the equations guiding the formation of these structures imply that there should be about 100 of these tiny dwarfs around each of these big galaxies. And so that might be the key of what we're seeing with these streams of stars, is that maybe there were 100 of these little dwarf galaxies and they've all been eaten by our galaxy to this point. So it's not well understood, but this is sort of what our local galactic group looks like. And this group, if you step back now, this is a little further than that video, or a little closer than that video took us. This is the Virgo cluster. This is the Virgo galaxies, and our local group galaxies make a cluster. So we have stars, we have star clusters, we have galaxies, we have groups of galaxies, and then we have clusters of groups of galaxies. So it's a classification that's going further and further out. And then at the largest scale, we have this sort of imagery. And in the center is the Virgo supercluster, of which we are part. This blue line here is about 1 billion light years across, to give you a sense of scale. The Powers of 10 movie stopped about here, right? If we were in the center, Powers of 10 stopped about here. So not too far. What we know is a little bit further. And what's interesting here is because of how gravity works, and something called dark matter, which we won't talk about today, there's structure to this. You can see connections. And what's most noticeable to me is that there are also big voids where there is no galaxies or star formation, just emptiness. So emptiness and form, and emptiness and form, and emptiness, all connected as part of the large-scale structure of the universe. And so,
what do they say why those voids, then why material would coalesce in certain regions, and there would be whole areas where dust and all the matter would not coalesce and make sense.
well, it depends. If these voids are filled with dark matter, then that could be part of it. Dark matter is a word for something we don't know that interacts gravitationally. We can't see it. It could just be dark stuff that we can't see, but it behaves a little differently than dark stuff. So it could be something to do with this other kind of matter that we don't know about. Or it could just be a relic of time, that given more time, this structure will change. So this could just be a part of the evolutionary cycle. And so from here, 100 billion light years across, we come back to the Earth. And so just sit for a minute again. So we started just sort of sitting. Leaning against the wall is fine. Just sit for a moment. You can close your eyes or keep them open, whatever's most comfortable. And just watch the breath for a moment. You don't have to think about anything we said. Just watch the breath moving in and out. And as you take a breath in, make a little bit of space after that inhale to just stop for a moment. You don't have to hold the breath in, but just feel open in a space of vastness. And then after that pause in the breath, let the exhale come. And after that exhale, give a little space in that still point before the inhale begins, in that empty space. And again, finding the inhale, the space after inhale, letting the exhale come, and stay in that space after exhale. And continue breathing. And as you breathe in, imagine this vast, infinite nature of the universe coming closer to you. The infinite vastness of the universe approaches you as you inhale. And in this pause after the inhale, this infinite vastness of the universe resides within you, just for a moment. And as you let the breath out, feel yourself expand into the infinite vastness of the universe. And in this moment after exhale, let yourself be empty and connected with the deepest, furthest parts of the universe. So inhaling, the infinite vastness of the universe approaches you. Holding the breath in as the infinite vastness of the universe resides within you. Exhaling into this infinite vastness and resting for a moment in this spaciousness. Just continue to breathe. And so this dichotomy with spiritual practice and astronomical physical learning that I felt existed because I was looking for the same kinds of answers from two different paths. And what I've come to feel in my own practice is that the learning of science helps you study the universe, and the spiritual practice helps you experience it. There's a subtle but distinct difference, which is both complementary and different. So we complete here with the nature of form, and as an introduction to next week, I just want to share these words from Carlo Rovelli. The difference between things and events is that things persist in time. Events have a limited duration. A stone is a prototypical thing. We can ask ourselves where it will be tomorrow. Conversely, a kiss is an event. It makes no sense to ask where the kiss will be tomorrow. The world is made up of a network of kisses, not of stones. But we talked about stones today. Next week, we'll see if we can verbalize kisses. So, thank you.